All right, so let's talk about the least squares regression line. This is something we learned about in Algebra 2. The least squares regression line is also called the line of best fit. When we find the line of best fit, usually what we're trying to do is we're trying to draw a line through a scatter plot so that there's the same number of points below the line that there are above the line. So I could try that here. Draw a line, and that looks pretty decent. So I have maybe 2 points below the line and 1 point that's definitely above the line. The rest are pretty close to being on there, so not too bad. So with the line of best fit, the reason why we want to have this is because using this line, I can make predictions about data that we don't have, about explanatory variables that we don't have. So like, for example, before I drew that line there, I only knew about the temperature at 12 chirps per minute, this is maybe 15 chirps per minute. This one looks like 30 chirps per minute, and so on. I only have data for those points. When I draw my line of best fit, I can now make predictions for, say, what's the temperature when there are 50 chirps per minute. 50 chirps goes to the line here, which corresponds to 50 degrees Fahrenheit. So even though I don't have a data point for 50 chirps per minute, we can make a prediction based on this line of best fit. So with the line of best fit, we have our predicted values and our actual values. So again, backing up, with just the scatter plot, we have actual values based on actual data that we actually observed. So the actual values are the y values of the actual points in the scatter plot. The predicted values, the values we predict to be true, are the y values on the line. So the line of best fit, that pink line, any point that's on that line is a prediction. We don't know for sure it's going to be true because we haven't actually observed anything at those points. But we think it's true because our data seems to follow that linear pattern. So as you might notice, there's a couple spots where our actual data deviates from our line of predicted values. So like here, it looks like it's about maybe 65 chirps per minute. We have a point with an actual value here, looks like about 55 degrees Fahrenheit, but on the line it's different. It's more like 53 degrees Fahrenheit. So it's possible for our predicted value, of course, to vary from our actual value if our points aren't all on that line. So that's when the residual comes in. The residual is the actual value of any point in our scatter plot minus the predicted value of that on the line. So for this, we said this was maybe like 55 chirps per minute. So the residual when x is 55 would be 55 degrees Fahrenheit minus the 53 degrees Fahrenheit on that line. So that would be a positive 2. The residual at that x value is positive 2. On the other hand, if I come over here to, say, this section here where that's about maybe it's like 13 chirps per minute. At that point, I can see I have an actual value around maybe 37 degrees Fahrenheit. And my predicted value is different. On the line, it looks like it's closer to 40 degrees Fahrenheit. So the residual there, again, you always take your actual and then subtract predicted. So the actual in that one is 37, that's the point of the scatter plot, minus the predicted value on the line, 40, gives us a negative 3. So it is possible for the residual to be either positive or negative. In fact, if you notice, when our residual was positive, it's because our point of our scatter plot was above the line of best fit. When the point in our scatter plot was below the line of best fit, we got a negative residual. So if your point is below the line of best fit, your residual will always be negative. If it's above, your residual will always be positive. So with the least squares regression line, it's not just any line that we can draw through a scatter plot. It has to be very, very, very close to all of our points, or as close as possible to all of our points. And the reason why we call this line of best fit the least squares regression line is because of what you see here. In both of these scatter plots, we actually have the same points. You look at the blue dots themselves, they're in the exact same position for both scatter plots. What's different is the line. For the one on the right, the line is drawn pretty far away from a lot of our points. And therefore, when I take my residuals from any actual point to the line, I get a pretty big segment. So what they do then is they actually square each of those residuals here so that we have a picture like this. And the reason why we square these residuals mathematically is because it gives us, when we square something, we always get positive numbers. But visually, it gives us a really nice picture of how far off this line of best fit is. We have really big squares in this picture, which means there's a lot of space between our actual points and our predicted points on our line. Whereas on the left, my line of best fit is actually pretty good. I do have a couple points that are a little off. The residuals are a few points, but when we square them, for each residual, if we square every single residual in here, we're still not seeing that much green. So the least squares regression line is the line that minimizes those squares. It literally has the smallest possible squares formed this way. So I would say the least squares regression line is the best fit because it has the smallest squared residuals. Okay, so that's how it gets its name. So it's when we're sketching a line through a scatter plot like I did up here, it's possible that the line I drew isn't necessarily the best line. So because of human error, we can't actually get a least squares regression line just by drawing it. So we're going to use a graphing calculator to get us a regression line, a line of best fit that truly is the best. Before we look at the calculator, though, let's talk about the formula that we use for the least squares regression line. It's going to be the same formula that we're going to see in our calculator, and it's going to be the format that we need to write it when we give our answers in any type of test. So the least squares regression line formula is y hat equals b naught plus b sub 1 times x. Okay, so before I talk about what each of these letters mean, you've actually already seen this type of formula before. This formula is actually no different than the slope-intercept form of a line that you learned about in Algebra 1. Think about it. The slope-intercept form of a line is y equals x plus b. If I rearrange those terms, I get y equals b plus mx. Now I can relabel some of my variables. Instead of saying y, I'll say y hat. I'll change b to a b naught, and I'll reassign m to be b1. Remember, variables can be represented with any letter or any symbol that we choose. A variable is simply a placeholder for a number. So they are actually the exact same formula. So when we're finding the least squares regression line, we are actually finding that line in slope-intercept form. It just looks slightly different. We do want the x term to be at the end in this case. It's just a statistician preference thing. So going back to the actual letters that are in here, we already know if this is the same thing as y equals b plus mx, then this is of course going to be the y-intercept. B naught is the y-intercept. And the number in front of x we know is the slope. So B1 is the slope. In statistics, the slope of the least squares regression line has its own special name. The slope of this special line is called the regression coefficient. Regression coefficient. Okay, so that's only for the slope of this specific kind of line. Next, we have that y hat. So the reason why we call it y hat instead of just y here is because remember, the y values that we get out of our least squared regression lines aren't actual values that come from our data set. The only y values that we know to actually be true are those that we observe and record in our data set. Anything that we get off of the line is simply a prediction, which means it may or may not be true in a real scenario. So y hat is the predicted value of y. And then of course x is the observed value of x. Okay, next, let's talk about how we interpret this slope and the y-intercept of the regression line formula. You've interpreted slope and y-intercept before in other classes, and it really is no different here. The slope, or B1, is how much the graph increases left to right, or specifically, for each one increase in x, we get B1, the slope, change in y. So if I put this in real terms, in fact, if I look at the actual scatter plot that I have here, say the slope of my line of best fit was, I don't know, 7. If my slope was 7, then I would say, for each one increase in chirps per minute, so for every one chirp per minute, there's an increase in temperature by 7 degrees Fahrenheit. So when we interpret our slope of our line of best fit, not only do we want to say it pretty much just like this, we want to make sure we say it in context. Don't say x and y, say chirps and temperature, okay? Same thing for y-intercept. We won't be asked to do this one as often, but when we do, we say that that's the expected value. The y-intercept is the expected value of y. And again, we say expected because we don't know for sure. It's just kind of a prediction when x is equal to 0, right? When x is equal to 0, we're on the y-intercept. So say the y-intercept of this thing was like here. There's the y-intercept. It's like 36 maybe. So if I needed to interpret that 36, I would say 36, we expect the temperature to be 36 degrees Fahrenheit when 0 chirps per minute have occurred. Okay, so when y is 36, x is 0, but make sure you say it in context. You shouldn't say x and y if x and y have a specific value that you know. Okay, next thing on here, something to be careful of, extrapolation. Extrapolation, this big giant word right here, is bad. We don't like to do extrapolation. Extrapolation is something you should not do. And of course, your textbook and your tests in APEX and the AP exam is probably going to ask you to find something that is extrapolation occasionally. So you need to be able to recognize it so that when somebody asks you to do it, you can say, no, that's bad. We don't do that. That's extrapolation. Okay, so what extrapolation is when you predict a y value that's outside your observed domain of x values. So in other words, looking at this scatter plot here, my x values, my chirps per minute, we only have observations between, looks like that's like maybe like 12 and 90 chirps per minute. So when I use my least squares regression line and I'm making predictions for points that are on that line, I need to make sure that I'm only making predictions for points that are between 12 and 90. And they gave a great example of why you don't want to do this in the APEX video for this section. I forget the actual numbers that they say, but they say something like, if you were asked to find the temperature when this grasshopper had chirped 200 times, the line of best fit, you could use your calculator, and your calculator would tell you for sure that, oh, that value would be, I don't know, like 180 degrees. And that point, 200, 180, is truly on your line of best fit. But it's not a valid prediction. And if you think of it, of course it's not. At 180 degrees Fahrenheit, that grasshopper is probably going to be dead. They're probably going to be boiled and crispy. That is way too hot for a grasshopper. So again, that's why we call it extrapolation. We can only make predictions for a given domain of X values. Anything outside of that, whether it's below or above, we cannot do. So when they ask you to, you just have to say extrapolation. That X value is outside of our observed domain, and then move on. All right, so let's go ahead and talk about now how to actually get our least squares regression line on our graphing calculator and then use it to answer some questions. So the first step to getting our least squares regression line is, of course, we need to actually construct a scatter plot, and we did that in 3.1. So just a quick review of that. I take my graphing calculator, I put the data in my list, and that's the data from this table over here. I put the data into my lists. I go to my stat plots by hitting second, y equals. Make sure all my other stat plots are off except for the one I want to work with. Turn it on, choose the first type, that's a scatter plot, and make sure your X list and your Y list correspond to where you put your X values and your Y values in your lists that we just created. If you need to change either of these to like L3 or something, we can get those by hitting second and then the number of the list that we want. If I wanted to change this to list 3 for some reason, I would hit second and then the number 3 to get L3. Now I'll change it back to second L1. So after I have it all in there, I could go ahead and graph it, but I'm just gonna skip a step and go straight to zoom. Well, I gotta clear out of there first. Zoom and choose option 9 real quick, which is gonna zoom in the best my calculator thinks it can for the statistics that I just put in there. So zoom stat, and there is my scatter plot, okay? The next step on here, and this is pretty important, it says, does the data appear to follow a linear pattern? If you look at your data and it appears to be like pretty obviously curved, then we don't want to use linear regression. Think about it. If I have a scatter plot and I put it into my calculator and it looks like this, that's a crazy scatter plot. That looks like a parabola, right? It does not look like a line. If you were to ask your calculator to find the line of best fit for that scatter plot, your calculator is going to do it because it doesn't know any better. It'll say, oh yeah, sure, that's this. But that's obviously not going to give us good predictions for this data because this data follows a quadratic curve, not a linear curve. So you have to make the decision before you calculate your line of best fit, what kind of line do you need? If you make your scatter plot and it's not linear, you cannot do this type of linear regression. We would need to do quadratic regression here actually, and we're not going to get to that in this section. So I would simply say that the data is not linear. So we would say the least squares regression line is not a good fit for this data. And if you're worried about, maybe you're taking the actual AP exam and you're worried about getting counted off for not giving the actual regression line when they ask for it, I would give the regression line that your calculator gives and then make a note underneath that that says this line is not going to be a good fit for this data because our scatter plot is not linear, okay? So even if you give that answer just to be extra safe, I would still make sure you write down that that's not a good fit because the data is not linear. And we'll talk about quadratic regression and how to make your lines linear later on, okay? So for now, going back to what we actually have for this example, I would say that does appear to be pretty linear. It looks like it's starting up towards the top left and working its way down to the bottom right. So as far as we can tell, it looks linear. All right, so now let's do step 3. Now that we think it's probably linear enough, we go to step 3, and there's your step-by-step instructions to get your line of best fit. So you hit the stat button. Stat is right here. Move over to calc by using the right arrow, and then go down to option 8, or you can just click the number 8. It's lin reg a plus bx. Notice for option 4, there's another lin reg ax plus b. That's will give you pretty much the same thing, but of course the ax plus b isn't the format that we want. We want a plus bx, and that will always be the case for statistics. So I hit enter. Make sure our X list is where we have our X data, L1. Our Y list is where we have our Y data. Frequency list is not something we need to worry about. Store reg EQ, though, is super helpful. What this line right here does is if I put a Y vars in here, and I'll show you how to do that, it will automatically store the line that it's about to create in my Y equals right here, so that I can graph it and even calculate values for it very fast. So in order to do that, I'm going to go ahead and click vars, go over to yvars using the right arrow, choose the first option, function, and I can see all of my Y numbers here the same thing that I see when I click the Y equals button. So I'm going to choose wherever I want it to put my equation. I'll just say y1 because I don't have anything important there right now that I'm worried about losing. And then I'll hit calculate. And this is what I see. So notice, sorry, on your note guide here, it looks a little bit different. This is what it looks like in a TI-83. I have a TI-84. If you have a TI-83, when you first go calculate, move over to calc and choose option 8, lin reg, you'll just see this on your main screen. And then you need to add to that L1, indicating where you want your X values to come from. And then you have to add a comma. And then you add L2, which is where we want our Y values to come from. And then another comma, and then Y1 from that vars menu again. So either way, once you put that in, you should be able to see the line of best fit, the least squares regression line. It says our least squares regression line is y equals a plus bx, where a is 6 and b is negative 0.557. So that means our line of best fit is y hat equals 6 minus 0.557x. Y equals a plus bx with a and b substituted in. So that's it. That's our least squares regression line. Let's see. So the next thing it asks us to do here is to find a predicted value using the linear regression on our graphing calculator. So now to find a predicted value, let's go back to the calculator. And first of all, let's go ahead and look and see what can we predict. We can't predict anything. Remember, I can only make predictions for my observed domain of X values. So whatever I predict has to be between 1 and 6. If I were to try to make prediction for, like, say when X is 10, your calculator would say, okay, sure, yeah, it's -2. But that's extrapolation because it's outside of our observed X values. So we cannot do that. And generally, there might be some context that would make something make sense. So going back here, let's see, let's make a prediction for something that we can do, like maybe 3.5. That's in my observed domain. So I'm going to go ahead and go to my y equals here, and you can see, look, there's my least squares regression line that I just calculated. My calculator put it in there for me, and they even included every single decimal. So that saved me a lot of time that I would have had to do typing that in. So I can just go ahead and hit graph now, and actually, we have to make sure my stat plot, actually I'll leave my stat plot on. Remember, my stat plot that's on right now is a scatter plot of this data that I just found a least squares regression line for. So when I hit graph, it's gonna graph that scatter plot and the least squares regression line in the same window. There it is, and it looks like it is a good fit. So now to make a prediction like I wanted to do, I'm gonna go ahead and hit second trace to get to my calc options. And I'm gonna choose the first option, value. Let's calculate a value. And when it comes back to the screen, it says x equals what? Well, we want to figure out what is y when x equals 3.5. I put in 3.5, and it tells me when x is 3.5, y is 4.05. And again, that's on our line, so that's just a prediction. It could be right, it could be a little bit off. But we believe when x is 3.5, y will be about 4.05. So quick note here on your note, we did graph the line, and then we did second trace to get to your calc options, and then you choose option 1, value. Okay. Next thing, let's talk about calculating all the residuals. So we talked about residuals before. That's your actual value minus your predicted value for any data point in our data set. And we could calculate that by hand, but depending on the size of our data set, that could take quite a while. So since we have our graphing calculator, let's go over how to get all the residuals on our graphing calculator all at the same time. So the first thing that's really important that I want to say before I even go over that is before I can calculate residuals, before calculating, the very first thing that you have to do is you have to make sure that your least squares regression line is calculated, at least calculated on your graphing calculator. So you must calculate the least squares regression line. On your calculator. Okay, that's super important. So even if you're not asked to find the least squares regression line, you have to make sure that you use your calculator to find the least squares regression line before attempting to make your calculator calculate residuals. Okay, and the reason for that is because the residual numbers are based off of the values on the least squares regression line. If your calculator doesn't know what that least squares regression line is, or if your calculator has previously calculated a different least squares regression line, it's not going to know what values to compare your points to. So before I do anything to calculate my residuals, I have to make sure that I've done that stat calc option 8 ln reg a plus bx. Okay, until you've done that and you have that stored in your calculator, it does actually store that information in there, you cannot find the residuals. So since we've already done that, I can go ahead and show you the next step. So once you've calculated a regression line, you go back to your stat button and we go back to edit. And this data should already be in there because you can't calculate your linear regression without having it in there first. So now I'm going to go over to L3, and actually I'm going to go up and actually highlight L3 itself and click enter. Now my cursor is over here next to L3, and I'm going to put in residuals. I'm literally going to put in residuals here, and that can be found by going to our list option above stat. So you got to click second stat, and then all the way at the bottom, see here option 7. RESID is short for residuals. So I hit enter. And now it says L3 is equal to the residuals. So I hit enter. And bam, all my residuals have just been calculated for me. And they got lots of decimals in there. Let's see what's next. Residual plot. Okay, so a scatter plot that displays a relationship, a residual plot is a scatter plot that displays the relationship between the residuals and the explanatory variable, x. So a normal scatter plot shows the relationship between your explanatory variable and your response variable. So we're going to go back and we're going to change our response variable to be the residuals. And when I look at this residual plot, which is a scatter plot of a sort, if it follows any kind of a pattern, then we can say that that regression line is not a good fit for the data. So I said before, when you make your scatter plot, you always want to look at your scatter plot and ask yourself, does it appear to be linear or not? If it appears to be linear, then we can go ahead and calculate our least squares regression line. But if it appears to follow some kind of other pattern that's not linear, then we would say, wait, hold on, this doesn't really look linear. I don't think I should use linear regression. We need to use a different model. So after I've already calculated my least squares regression line and I've calculated my residuals, this is another way that I can double, triple check that my linear regression line is really a good fit for my data. So I'm going to go ahead and create a residual plot using my graphing calculator. Let's go ahead and create a residual plot for the data that we just had in here. For this last example that we just did, we just got done calculating the least squares regression line and the scatter plot and the residuals. Now I can actually pretty easily switch gears and look at the residual plot. All I'm going to do is go back to my stat plot, second y equals, open this plot back up, enter, and it still says it's on and it's set to a scatter plot. I'm just going to change my y list from L2 to L3. Remember, L3 is where we just put all of our residuals. So now I'm going to compare my x values in list 1 to the residuals in list 3. And of course, my line of best fit is still in there, which isn't really relevant right now. In fact, I'll go ahead and clear that out. I'm done with it. And let's zoom into our plot. So zoom 9 to get our stat plot zoomed in. And there it is. So we would say the residual plot appears to be random and have good spacing. So I would say linear regression is a good fit. So the line of best fit that we already found the formula for is still okay to use. Let's look at another example now. Let's look at this one. I'm going to put this data into my calculator and find the least squares regression line and see if it's a good fit using the residual plot. All right, so here I have my data in my list, and I'm going to go ahead and create a scatter plot for this data real quick just to make sure that our line's going to be just to see if our line's going to be a good fit or not. So I want to make sure it's a scatter plot and it's comparing list 1 to list 2. Oops, list 2. And that's what we get. And it looks like it's pretty linear. So I would say, based on what we have so far, I think going with linear regression is pretty good. So let's go ahead and before I can do my residual plot, I have to calculate my residuals. Before I can calculate my residuals, I have to calculate my least squares regression line. So let's do that. Go to stat, over to calc, option 8, lin reg a plus bx. Make sure our data is coming from list 1 and list 2. The store reg EQ, with where you put that Y1 there, that is optional. You don't necessarily have to do that. It's just kind of handy in case you ever need to use that line again. I don't think I need it for this problem at all though, so I'll just go ahead and skip that for now and hit enter. And there's my line of best fit, Y equals A plus BX, where A is 0.05 and B is 2.975. Let's write that down real quick. 0.05 and 2.975. Y, oops. Y hat equals, I already forgot it, darn it. That didn't work. Be careful or my computer's gonna freeze up on me again. 0.05 and 2.95. 0.05 plus 2.95x. So that's the least squares regression line that I got. Let's see if it's actually a good fit by looking at the residual plot. Remember when I looked at the actual scatter plot, it looks like a linear pattern is a good fit. Back here, a line that looks like it would work pretty well for this, but sometimes looks can be deceiving. So let's look at the residual plot too. In order to look at the residual plot, again, I gotta go to my lists and I gotta make a list of my residuals. So highlight L3, enter, second, stat, oops, second, stat to get to the lists, option 7, res ID, residuals, and enter. There they are. Now I can go back to my stat plots, go to my first plot, create a scatter plot for list 1 and list 3. And I'll just go ahead and second mode to quit out of that so I can go straight to zoom 9. And that residual plot appears to follow a pattern. I'm going to draw it. Residual plot. In fact, I'll write it like this. Yep. There's X. Yep. Here's our residuals. And it looks, I don't even remember exactly what it looked like, but it definitely looked something like that, which follows a pattern. It follows a pretty distinct pattern. It follows a parabolic pattern, which means that this line of best fit over here is actually not a good fit. So I would say the residual plot appears to follow a pattern so the least squares regression line, I'll just write it this way, the least squares regression line is not a good model of the data. Okay, so I could go ahead and even just go ahead and write, like, this is the least squares regression line, but it's not gonna fit this data very well. So, and that's it for 3.2.